All right, welcome. It's October 17th, 2023, and we're in our first discussion of Chapter 8 in Cohort 4. So, to begin with, what are just any thoughts or memories that you fellows have about Chapter 8? Just any piece that you remembered or anything about 8?
I was curious about the part where they talk about how movement and attenuation, like sensory attenuation, that was interesting to me where they, I hope I'm recalling this correctly, but it was like you didn't want to perfectly predict it at a certain point for like to perceive movement, which was interesting. Um, I don't know if I perfectly understand that, but uh, I kind of see an intuitive aspect to that, I guess.
Cool. Yeah, that's a very interesting section. Andrew, anything that you think
Um,
about? Yeah.
yeah, I guess I'd second an interest in sensory attenuation as well, because I guess we could get to that, but like box 8.1 is kind of the key bit of interest there. The relationship between precision, attention, and sensory attenuation. They seem to more or less equate precision and attention. Um, I guess the idea is you have some kind of belief that is, I am not moving, and you need to downplay or decrease the precision of that belief such that you can actually move in the first place. Otherwise, if you have very high precision, I am not moving, that kind of stays in place, and so you never actually get started on moving. Um, yeah, no, I thought that was really interesting, and it comes up a little bit more later in the chapter on how that kind of plays out, and the movement of limbs and such. So yeah, I thought that was pretty fascinating.
Yeah, totally. And like, where else does that apply? Like, can we understand the example they give with a motor behavior connected to the ActInf ontology? And then what other analogous um, sensory attenuation cases might be happening? Let's just see if it's been explored in a question. Okay. Well, we'll definitely look at this question about precision. And then here's the box 8.1. Okay, no answer. What's interesting about it, Ajith? Or what would you want to know about it? Or what do you, I mean,
I guess like it was just something where when I read it, it made sense, but I'm still trying to let me see if I can find it. It made sense. It was just interesting that we aren't like were they saying that the perception of movement itself, like in order to perceive movement, it was like we were decreasing how well we were predicting uh those
yeah,
states?
in order to generate movement, we must be able to ignore the sensory consequences, which is to say, disattend to it or attenuate to it
Yeah.
of that movement to form the initially false belief that I am moving.
Okay. Okay. Yeah, that's like just, I don't know, something about that's very interesting. It's so, and then afterwards, we are trying to make up for that by uh trying to predict those uh or get those appropriate like inferences, right? Um it's not, you're gonna start attending to it again, or is it you just decrease how much attention you're putting onto those states at first, and then after you're trying
Yeah,
to make up.
certainly it's an oscillatory pattern. So one analogy or another case for sensory attenuation is really important is the eye saccade. So when the eyes are fixed, the precision is high. So that changes in the visual scene when the eyes are fixed can be informative. And then during head movement and or eye movement, you kind of have like a hyperprior that pixel changes or are uninformative because they're not going to be very useful. You're expecting high volatility on when there's movement. So during that, there's like a sensory attenuation during the saccade. And then as soon as the saccade ends, it's just like re-engages attention.
Okay.
So it's kind of like when the signal to contract the bicep occurs, there's also a descending relaxation of the tricep in the kind of healthy setting. So it's not just like pull on one side and pull on the other side. It's like a joint contraction and relaxation signal. That's happening with two opponent muscles. Whereas the eye saccade attenuation example is more like opponent processing with a motor and an attention variable, but they alternate.
Okay.
So we have the eye saccade case with visual perception, getting out of a chair. Well, and there probably are other differences here. Like you could argue whether the eye saccade can, it's kind of like it's considering the counterfactual. Just like the getting out of the chair is, I am not in a chair, is the counterfactual. The eye saccade counterfactual is like, I am looking over there, but you're not. And so the belief distribution, ultimately you want to shift your location in that space. But if the current precision around the current state estimate doesn't have significant mass covering that counterfactual, then it can't be switched over to. So sensory attenuation relaxes the attention, expands the variance, reduces the precision, makes it so it's like, instead of like 99% sure that it's this way, you go, well, it's 80% sure that it's this way, 20% that it's that way. That opens the door to the counterfactual being realized through action. Just to kind of restate it a bunch of ways, because I think if it is the case that that's how attention and attenuation work, then probably it's going to be prevalent in like every sensory motor system. Because the alternative would be constant precision.
Yeah, and then so constant precision would actually make you less likely to um be able to process movement, because there's a lot of it's almost like you're be able like less likely to get new information. Is that kind of a way of thinking about it? Is that why we're kind of relaxing the attention so we could be more flexible with sort of uh states that are changing very rapidly?
I think that's true. So let's think about what would happen if you had constant precision. Constant precision to your visual field in the isochate or constant precision to your proprioception for the getting out of the chair case? Well, when your eyes were moving, just where would you fix your constant value? If you fixed it at the level of that your surprise should be at for being fixed, then it'll be shocking when there's movement. If you have it when if you calibrate to when the pixels are moving a lot, then you won't be able to glean as much information when they're not moving because you'll be disattending. Or you could pick a lukewarm value and kind of blend those two, be a little bit more surprised than you should be when it's surprising, and then a little bit less informative when your gaze is fixed. So obviously, an approach to resolve this tension is to have oscillation or some kind of conditional attention so that you can tune it and do the best you can do in each moment instead of trying to like fix a value when we already know that there's a different optimal precision for different settings, or like through time within the same setting.
Okay. That makes sense. It's kind of like trying to think of a good sort of analogy, but just like you're actually doing worse by, it's kind of like, you know, you're grasping, like, have you ever heard of that analogy where you're grasping like a seed? You can't hold too hard or it'll like slip out, but if you hold it too loose, it'll also slip out. So you need to like adjust.
Yeah, that's good connection. That's also related to kind of optimal grasp. Like optimal grasp on a pen is not the maximum compressive force for a variety of reasons. You know, you'd be exhausted, you couldn't have dexterous movement or something like that. So like then that's related to like not over or under fitting. And that's kind of the VFE imperative, which is you want to fit a distribution given the family of variational distributions that you're choosing from, Gaussian or whatever it is. You want to parameterize it so that if you were to make it any tighter, you'd be overfitting. And then if you made it any looser, you would be having left information that you could have used. So it's on some trade-off frontier, which we can be along with a KL divergence. So it's like it's, you know, it's in a good spot and it's on a good optimizable manifold that if the variational family is at all appropriate, you're going to get to the optimal grasp. Now, maybe it's like trying to do optimal grasp on something that's too small or too large to be grasped. That would be like if the distribution family was inappropriate. Then you'd come to the best grasp you could of, you know, the mountain, but it wouldn't be possible to actually do it. So that kind of connection, like the model that doesn't under or overfit still may have an adequacy of 1%, given the data and all this other things. And then one other connection there is like the Kalman filter or just generalized filtering. So we're getting measurements from the thermometer through time, one or more thermometers through time, and then we're tracking the temperature distribution, or stock prices or something. Then you want to be tracking both the expected mean temperature and the variance, like the volatility or just the uncertainty, the sort of fundamental uncertainty or volatility, and then also the measurement associated. So the measurement associated volatility is more like A matrix. The actual dynamics are more like B. But to whatever extent it comes, the noise or the variability comes from either the sensor measurements or the underlying dynamics of the system, you want to be fitting this curve through time such that new noisy data measurements are not like falling outside the curve, because then that's more surprising than it should be. Then you should widen the curve. Or if all the data are falling like within the plus or minus 1 standard deviation on the curve, then you could have done better by tightening the distribution. Sanjeev's work on the generalized filtering is really nice on this, on the generalized filtering, kind of connecting it to the Bayes Bayesian optimal filtering in perception and then bringing in action.
This also kind of reminds me of exploration, exploitation trade-off and reinforcement learning and soft value functions, where they actually, instead of just trying to optimize a reward, they try to also increase the entropy, like an entropy value. So, which seems kind of counterintuitive, but it's actually performs really well. It makes it very flexible and able to deal with perturbances specifically. So like disturbances, like if you have a robot that's trying to work in an environment where things can start disturbing it and things like that, having sort of that, like trying to optimize that entropy value as well as the reward value, makes it so it can actually adjust and deal with disturbances a lot better, which kind of reminds me of like movement also. It's kind of like disturbances to sort of your...
Oh yeah. And there's two kinds of motor disturbances: ones you have agency over and ones you don't have agency over. Which ones are more surprising? The ones you don't have agency over. Like you can not a recommendation, but you can slightly push the eye so that it's kind of like a non-saccade induced visual shift. Of course, that's surprising. Or if you can't tickle yourself, because the expected proprioceptive consequences of tickling yourself are not attended to because they're expected, so they're confirmed. Or yeah, just how we expect, how far do we expect the stare to be? If it's a little bit more or less, then it's surprising. So then just the expected consequences of action are normalized too. I mean, sensations are perceived, calibrated to what their expected states are. This is kind of the whole predictive processing. Everything is like sensory attenuation is kind of a corollary of a first principles corollary of this kind of action and perception as inference. And then it just like predictive coding in the visual system, this is empirically found in different systems. And then it'd be interesting, like what other phenomena are, like where do we see allostasis or attenuation in other systems? Like if you have the bacteria in the gradient of sugar, or like antibiotics or something, it recalibrates to the value with like a kind of log sensitivity so that it can always have optimal grasp on making a decision about the gradient. If the gradient were 1,000 times longer than the bacteria, it couldn't detect it. If the gradient was 1/1,000,000th of the wavelength of a bacteria, it couldn't detect it. But then there's some range that it can actually do the calibration that gives the most statistical resolution, just like the aperture of a camera or the noise level of a sensor. And so then when you're calibrating the microphone or the whatever it is, the two minimal things, or the one minimal thing is just the mean. that's like the delta, the Dirac delta function is if you can only estimate one parameter about to calibrate the microphone in the room, you would want to know the potentially the average or the mean of the median volume. And then the second thing would be a variance parameter. Those might be jointly estimated for certain one parameter families of distributions, like Poisson distribution, where you only use one parameter to describe the family. And then that is like where like the mean and the variance are equal, is a one parameter estimation. But in either case, the kind of two that are helpful are the central tendency and then the variance. It doesn't have to be Gaussian, but you kind of need those two, because if you don't have a measure of this of a central tendency, and then how wide a field of the central tendency, then it's like you're kind of saying that it's a diverging situation. So then it's not really identifiable. Good stats pieces. All of regular, these are common topics in other statistics settings. And it's kind of cool because like they're often discussed in the signal processing inbound passive inference side, Kalman filter, all the variational autoencoder, and then also in a kind of slightly siloed way in the control theory, optimal control, KL optimal control way. So then those two statistical problems can be understood as kind of like two complementary special cases. There's optimal signal processing when you have no agency or no action control. And then there's optimal control in a completely known environment where there's no epistemic value, which is like the figure from earlier with showing expected free energy, and then when certain things are included or not, what the special cases results. So sensory attenuation, it's a useful tractable motif that does that addresses the kind of realistic statistical problems by modulating and learning attention.
Another thing I was curious about was the generalized synchrony, where they're talking about the birds doing the bird song, and then the other one would try to finish the other segments of the song. It just kind of started going into something I'm like been interested in, which is like communication and even like linguistics, and just like how that seems similar to communicating language. And like when you talk to like a language model, you're like a lot of people say it's just predicting sort of the best response or what's the most likely next response. And it kind of just reminded me of like this generalized synchrony where the birds are singing the song, and then the next segment of the song would be sort of, it's kind of like a response almost to the other bird if there's like two birds singing. Yeah, I guess I was just like curious in like how that and communication works. Like, is this like the very most basic form of communicating in active inference, like between two sorts of agents? Like, yeah.
Yeah, good questions. Andrew?
Oh yeah, I just wanted to. I previously skimmed a paper by Friston and Parr, and they actually reference it here at the bottom of 160 5, they built another model that basically has two agents, communicating with one another. And with synchrony, I'd rather go with the birdsong example, I guess, since it's more top of mind. But um, it's rather fascinating. There's this described like the birds are basically learning one another's model parameters, right? Such that they start making virtually the same inferences, one is with the other. I think this is a wonderful kind of example too, because I can imagine two musicians, wanting to play the same song, staying in time with one another, kind of following the same script or sheet music. Um, but yeah, I'll try to find that paper, just because I think it's, if you find interest in it, it's it's more based on potentially what humans would be doing. It includes an entire model of like how do you construct in communication, like what is a question, what are the different states involved with questions, asking one another questions, answering questions, and the like. So
I'd love to check that out. Yeah.
Yeah, that's cool. Yeah, you even said like scripts, and Albaros and et al. With the strong and weak scripts. So you have two musicians, they could literally have the same sheet music, and that could be truly isomorphic sheet music, like they're both playing the first trumpet part on this one song at the same time. It could also be a general synchrony, which is to say not necessarily a lockstep, maybe it's a call and response. So there's still a perfect mutual information between the two sheet music readings that are ongoing, even though they might be playing different instruments or they might be playing different parts. So that's like what in that birdsong example and subsequently they've referred to as like the singing from the same hymn sheet. And then kind of stepping out into the improv is another step that I know some music and other researchers are interested in, because like with questions or just other turn-taking mechanisms, because obviously it's different when there's epistemic transfer in communication of whatever kind versus just the co-performance of something that's fixed ahead of time. So that's one key piece. And then the point about the large language models is a really good one. So the likeliest continuation of this trained model, it's almost like the current token is Y, that's the observation. And then we have like Q, big foundation model Q. Now, it's not necessarily a variational Bayesian model, but then there's going to be some variational free energy landscape. And then when the temperature is low, it picks simply the next likeliest outcome. And then as the temperature increases, you flatten that landscape so it starts sampling like more broadly to the point of breaking out of kind of semantic ruts, but decreasing potentially like the fluency or the coherence. So that's like we have the path of least action, and then we have that temperature or shaky hand parameter, because in language, selection of topic and sentence and word and phoneme and all of that is like this nested policy selection task. And then so we have both the path of least action, that's kind of the ridge on the bottom of the valley, and then we have this like sampling technique where you can sample along the strictest likeliest path of continuation, or you can sample more broadly like from that valley. So it's an example of how like statistics or active inference approaches could be taken, even if GPT-4 or whatever doesn't need to be applying active inference from the inside, but we could still talk about its expectations or preferences and how that conditions its actions and all these different aspects, but it's mapped on territory. So we'd be doing like cognitive mapping of GPT-4, not reverse engineering or engineering from the inside. So the birdsong example is a singing from the same hymn sheet example where there's an expected, and so it's an interesting and a good continuation from the sensory attenuation. They both have this an expectation in their generative, each bird in its generative model of how the song is supposed to go. And then the question is, are they going to be singing that song or not? And so in this example, it's like, well, like someone should be singing it this way. And then it finds itself singing. And then as it continues to sing, takes its turn, its precision drops. We could talk about why precision might drop through time. And then eventually that leads to a consideration, hey, maybe I'm not the one continuing this song. And then that's like the kind of turn-taking mechanic, but it's not the only turn-taking mechanic that you could design. You could use like a stop, word like over or something like that, or start words, or you can make any mechanism. And then I think they show in that first paper with Friston, Frith, or in some other papers, like maybe what one of you mentioned about like the learning of the model. And in that case, there was like a younger bird, like a more plastic bird with lower precision. And then over multiple rounds, it learned how the song was supposed to be. And then the first bird was taken away, and then the new one was added in. And they showed that basically you could do like this successive passaging of entrainments in the generalized synchrony setting.
So they mentioned like this leads to the birds trying to like match their internal models by trying to match how they continue singing. And I definitely want to check out like how it was like all of this was like how Friston and all of them connected this to communication. Because like I guess I'm like wondering like how you communicate bits of information directly, because like it makes sense. You match the internal models and then you I guess like you take turns and you communicate the next section, and then I guess what informs the other bird, just like from like a sort of base like information theory type perspective, it's like now the other bird knows that they're singing the same song. I guess that is like some information that's being communicated. And then, yeah, it's like matching the same song. And then I guess that is kind of like an analog for language. If you consider every idea or concept a song and you're trying to match with the same concept, or like some communication that you're trying to communicate.
I think there's
Yeah.
some I was just gonna say, I think there's some theory somewhere. I don't want to misquote someone. I think it was from a neuroscientist. But the idea that whenever two people are communicating, it seems to be the case that, including using like neurophysiological measures like EEG or otherwise, that there tends to be an increasing kind of synchrony between them. That includes in the kind of spectral dimension, like frequency. Like if you did like a spectral decomposition of the EEG and look at the frequencies going on, like their frequencies tend to slowly begin to match one another. And furthermore, if you kind of analyze the contents of the conversation, which I'm not quite sure how you do this with high precision mathematically, but the idea is like two people communicating with each other are slowly reaching some kind of convergence or consensus in what the conversation is about agreements upon the topic. Even if you disagree, at some point you do converge in the idea of, well, now I know your stance and I also know my stance. So at least that kind of truth has been converged upon. So I guess to sum it up, like communication is some kind of general the process of convergence or synchrony of information, of brain frequencies. And I guess here with chapter 8, synchronization of chaos, because I guess we haven't really gotten into that, but like using the Lorentz system as one potential like continuous model as well. Just sharing all that. Yeah.
That reminds me of like how communication in like Wolfram's Ruliad is sort of like between observers is kind of explained. It was like between the observers they have like shared like segments of the Ruliad that they could both like kind of agree upon. Which kind of reminds me of sort of like trying to match your internal model. Or, you know, like what you were saying, like at least you converge that you both are some understanding, even if it's on an agreement. It's like you're converging on how your stance is related to the other person's stance, or like that relationship itself is kind of like a concept on its own, which is very interesting.
It's like we're putting both of our cards on the table. Now we can see each other's cards, so to speak. Like that information has not been shared. Right? Even if the information that you brought to the table was different, right now you've kind of come together here. You have shared information, and furthermore, you are in an instance of a particular conversation, right? So it's
yeah. And like in information theory, like communication channels, it's kind of like you're trying to I mean, a lot of this chapter reminded me a lot of communication channels from information theory, just like trying to know what the original input was that goes across a channel, and then you get an output, but the output might not be the same as the input, and you have to see if it matches. And if there's noise, then there might be some variation with the output. So it's just kind of like trying to decrease that noise. And then that's why you calculate the capacity of what's sort of the max rate of bits you could communicate across this channel without sort of where you know for a fact that you'll be able to map it directly to sort of the original input or like the cause. So
yeah, a ton of great connections. I think it's going to be really exciting to see the quantum FEP, Crisfield's semantic information flow meet up with the Wolfram Ruliad. I think that should be impending. And yeah, and then there's kind of like the agent environment communication. That's Alice and Bob. And then sometimes we can kind of take the Alice as agent, environment as agent, Bob as agent, and then just sort of like summarize it with just the holographic screen with the classical information, which is kind of like saying that there's an inert intermediating entity. So quantum on either side of the boundary and classical, or n dimensional on the boundary and then n plus dimensions on in the quantum. And then there's simpler examples too, like having a bunch of metronomes on a table. So if the table is fixed, and then there can't be like force transduction amongst the metronomes, they will continue unabated with whatever population distribution is initiated. And then if there is coupling, non-zero coupling, then like that's the kind of famous videos where they enter into lockstep. They're simple or conservative active things. So the general synchrony that they come to is like either all aligned or a two-phase, but then I've also seen it where it's two-phase and then it kind of falls a little bit off and then it actually slides all the way to back to lockstep, because that's a slightly more favorable synchrony. But they're all exact versus one where say it's like 50-50 or 99-1 with one going in the counter phase. So that's kind of like the simplest generalized synchrony. And then it's a huge open topic with semantics and linguistics. Seems like there's a lot of information in the sequences of tokens. How many bits, how many nats relative to what? But also it's not just the sequence of tokens. We know that in our generation of language and our seemingly our perception that, of course, the timing, the tone, context, all these other features come into play. So then what is their mutual information? And there's settings where maybe just the tokens are necessary and sufficient. There's another situation where the token, there might not even be a token, like a silent sign. What does that say? So then, yeah, these are great questions of communication. I think we'll continue to see, like, in a lot of different fronts, like ratcheting of the, okay, now sophisticated and the affective. And then they have these models of the nested. Look at this. This is like figure 4.3, identical on top. And then the bottom, whereas in figure 4.3 in the textbook, the bottom is the continuous time GM. Here we see the discrete time GM converted into the Forney factor graph. And that supports the message passing more proximally. But we're dealing with this exact same discrete time model. And then, as we see with like the folk psychology models, often the more cognitive or symbolic tasks are discrete. And then the hybrid model is like where it hits the ground, it's continuous. Like, for example, the larynx contraction or voice box or lip or tongue might be a continuous time, continuous actuation model. So you have some continuous voice apparatus with the proprioception and the actuation making phonemes. But then once you're in the space of identifiable phonemes or lexemes, then you can be at this level where they're now making discrete time models at the symbolic. So they've abstracted away from the phoneme. They're not dealing with that here. I'm saying that's kind of implicitly underneath it. They're just saying that they discretely produce and recognize these words. But then that's what's so nice about the composability of ActInf. Okay, now here they're taking it deep. We see that 4-3, but now there's each time step has 3 nested. So that's discrete within discrete nesting. And then you could also just say, instead of the observation being a discrete token, you could plug in a continuous model there. And then you could evaluate, empirically, or what are the computational requirements, or where are you getting more value add? And I think, well, the chaos thing, that's explored a lot in the stochastic chaos and Markov blankets paper. I think 34, live stream 34. And then it's interesting how, like, even though a lot, and I think Thomas Parr may have remarked on this in the book stream 2.1, like the earliest ActInf models were the continuous time. And then to accommodate classically symbolic cognitive processes and also explicit planning as inference, and also to integrate with the POMDP, well known in planning, there was a movement towards the discrete. And then there's DaCosta et al. 2020, like a synthesis of active inference in discrete state spaces. So not like it's like finished and people continue to develop new motifs and discrete compositions, but kind of like the fundamentals of the discrete were then focused on more. And then potentially now with the path-based formulation of Bayesian mechanics, G theory, everything that Dalton and Maxwell et al. Are working on, there's kind of like a renewed emphasis and generalization on continuous structures like paths, sheaths, bundles, topos. things that the book doesn't necessarily go into, but sets the stage for. And then figure 8.6 kind of like shows in the simplest possible example, which is the same one that livestream 46, the ActInf does not contradict folk psychology, the simplest hybrid model where you have a discrete higher level symbolic dimension, and then this kind of like sensory motor continuous time. So this is like figure 4.3 gets smushed together. And then, yeah, I mean, just in terms of the location in the book, second half is the more pragmatic model, construction and implementation based focus, starting with chapter 6 with the recipe. And then just like the low and the high road were sort of this dialectic that are unified or contained, of or by active inference. In 7 and 8, we have that distinction. And then again, with this figure 8.6, by the end of chapter 8, we're already landed with the synthesis of 7 and 8. Whereas 2 and 3, they really are like different branches and they meet in the middle. And 7 and 8, it's more like, I mean, they're just tucked together at the end of 8. And then chapter 9 introduces, okay, well, what if instead of specifying a GM, hashtag chapter 6, and then generating synthetic data, what if we already had collected data of a certain structure? We knew that we were going to collect data of a certain structure. How could we then prepare a GM that would recognize that data, allow us to do statistics on it? Whether we do discrete, continuous, or hybrid models, chapter 9, and then the end of the book. So just like so funny how second half starts fast, describes a few key, okay, here's the vertebrates, here's the invertebrates, or whatever. Here's the kingdom of the fungi, here's the other kingdom. Then chapter 9 gets more empirically oriented, and chapter 10 simply reviews and contextualizes active inference. So it's a quick ride.
It is very fast.
Yeah. Let's just see what the other questions were. How is figure 5.2 related to figure 8.4? 5.2, hierarchical predictive processing. 8.4, Lorentz synchronization. We should procedurally generate every single possible question. How is every figure related to every figure? I mean,
for a brief second, I thought maybe it would relate it to figure 8.1, which is a little more, I don't know, not quite message passing, but at least it's, we're still in the realm of looking at error terms, basically these basic equations with Lorentz. To go with Lorentz systems though, and relating that to message passing, I'm not so sure. There's no
yeah.
there's nowhere my brain quickly goes.
Well, that's the attenuated space where any account could be possible, or more accounts could be possible. Like, again, to this kind of question, prompt, question, answer, or even Hegelian problem, reaction, solution structure, it's interesting, like, which questions just have an answer, which ones are like the Grand Canyon, where the continuation, there should only be like one specific continuation. Like, what's the relationship between policy and affordance? There may be a formal answer, Not even to say that that would be the only answer still, but there might be a sumo expressible necessary sufficient answer, which is like pretty good. But then for any question, but especially some of them, these questions are basically just evocative, which is totally fine. I think it's fun. We're only going to experience even just with a 30 or 50 or how many figures there are. I mean, that would be like 2,500 questions.
Mhm.
So just like then, so that's the epistemic foraging. Which questions should we ask? Prompt engineering, conversation theory, all these different things, like folding back into the way that we're learning ActInf. Like, okay, now that we've looked at what are the causes and consequences of sensory attenuation, now what are we going to pay more or less attention to? Or now that we've talked about communication along these lines, then how do we do what? A lot of fun options there. Here's the improvisation question. Yeah. I'll just move it to this one. Any last thoughts?
Yeah, so in chapter 9, is it more about like using active inference on sorts of like if you wanted to use it on like a data set and to detect something or things like that?
Yeah, basically it points that way. It is not the guidebook or the Google Colab notebook or whatever that just, oh yeah, load in your CSV and then this is just going to analyze the data for you. So it's not to that point. But what I think 9 does that's important, first, 9.1 is a schema of the behavioral scientific setting where you have a behavioral science laboratory making a cognitive model of the rat or the ant or whatever, which might be a map back of the environment, but it frames it in a way that we can handle with ActInf. And then, analogous to how chapter 6 gave a recipe for making the GM, figure 9.2 gives us the roadmap from going from the data plus the GM to basically the kind of figure that would be in a published paper. Like, we proposed a personality variable or a psychometric variable of this kind, continuous or discrete or whatever it was. We had the generative model, we had these data and likelihood function. We inverted the model in light of our prior beliefs, which might be uniform across groups or whatever it was in the setting. And we think, and this is kind of like Ryan Smith's precision psychiatry work, you'll see a ton of things like this. It's like, and people who had this or this categorization or this or that continuous variable, here is the correlation or the regression between our inference about this parameter and whether or not they were diagnosed this way. And here's the t-test, and it looks like something that you'd find in a paper. In other words, supporting an empirical claim, being part of a fabric of evidence about an empirical system, rather than just having a hypothetical GM and then speculating like it could be this way or it could be that way. Because, I mean, and until you parameterize it, and especially fit its data, because it usually could. So kind of like a 6 and 9, a little bit of a Jimi Hendrix thing. Okay. All right. Thank you, fellas. See you next time.
See you next week. Bye.
Bye.
Thank you. Bye-bye.